Science time.
What do you think about this conclusion?
Well, I want to do this right now, so I want to do this right now. Earth science time. Why? Guys, we could have talked about this. Oh, that's really good. I really like that. Let's start the video over. Okay, Earth science time. We're talking today about minerals. Is orange 2 not good enough? Please zoom in. I don't know. Orange might be 2 not good enough. Well, that word is minerals. I'm going to switch to a different color going forward. What is a mineral? Let's think about what are some criteria that minerals must be or must have? What are some criteria minerals must meet in order to become a mineral?
They must have crystals.
Okay. Crystalline structure. Crystalline structure. Explain crystalline structure. What does it mean on the atomic level? What's a crystal?
It's like little crystals that make up a mineral.
Yeah, on the atomic level, what does it look like though?
Like little tiny.
It's atoms. Everything's made, but it has to do with the arrangement of the atoms. How are atoms arranged in a crystal that makes it so it is a crystal? Yeah, they have their own special shape. They're arranged in what we call a lattice, which you would know from like first and second grade as a pattern. It's a pattern of atomic arrangement. A pattern of atomic arrangement. For instance, in the mineral calcite, which is a calcium ion and the carbonate polyatomic ion interspersed. I use this little circle as calcium. This slightly bigger, blobbier circle is the carbonate ion. This pattern, just like a pattern on a first grade class worksheet, is repeated over and over again. And furthermore, and this is why this is important, whatever the pattern is on the small scale, this atomic arrangement on the small scale, in this case a line, although that's not really the atomic arrangement of the site, whatever the arrangement is on the small scale, on the atomic scale, matches the arrangement in real life. So, 2 axes of perfect cleavage. Right? Quote me if I'm wrong, but it has some number of axes of perfect cleavage, meaning that the calcite cleaves on certain planes to form this rhombus shape, which I've done a pretty terrible job of drawing. But the atomic arrangement influences and is directly related to the macro arrangement, the macroscopic crystalline structure. And in fact, that's what makes crystalline cleavage and fracture such a good mineral, is because we define it based on their crystal structure, like because of its atoms that are in it. So this calcium form calcite. And when they're arranged a different way, which I don't know what it is, but I'm going to pretend it's a triangular prism, it's aragonite. It's the same exact stuff, same exact calcium and carbonate ion. It's just arranged differently. And I'm not trying to, the point here is not this. This is probably not the atomic arrangement of aragonite or calcite. My point is that even though they have the same chemical components, calcium and the carbonate ion, their arrangement of them makes them different in minerals. And because of that, crystalline structure is an excellent property to identify minerals, because that's part of what defines minerals in, but also what defines each specific mineral is its crystalline structure. What's the root word of crystalline? Crystal, yeah. It looks like a crystal. It's what a little.
What's that?
This is the word aragonite, A-R-A-G-A-O-N-I-T-E. You can look that up on MinDat, and it will tell you its actual crystal structure. Has a specific or a definite crystal structure. A definite crystal structure. What else must a mineral have? Or what other attribute Someone who isn't Camden think of it too. You'd read your explorations. You must have. What are the other properties? What state of matter must a mineral be? Solid. Your book, or I should say your exploration of the book, which is the same in material, it says ice is a mineral and liquid water is not because ice is a solid. In my experience and at the college level, we had defined minerals as they must be solid at room temperature, which means that even ice is not a mineral. The definition, as with any definition, is fluid when we get right down to it. For now, that it must be solid. Publisher of this book has generated, you could consider ice a mineral. In fact, I know for a fact there are those who do consider ice a mineral. I do not. I think that to say it's solid at room temperature is a better definition. We'll just put solid, and we know what that means. So I'm going to leave that one as solid. You all know what solid means. Does anyone not know what solid means? What's another property that minerals must exhibit? Sure. Can you think of another one, though? Is this a mineral? It's solid. Probably has a crystalline structure. I don't actually know. It probably is actually amorphous. Why not? This definitely has a crystalline structure, and it is solid. Why is this not a mineral? No, metals can be minerals. Not every metal is. Why is this one not? What's special about this? If I keep knocking on it, maybe you'll realize. No, what's special about it? Why is it not a mineral? Why is whiteboard not a mineral, Camden? Don't look anymore. Think of it. Yeah, exactly. It must be naturally occurring. It must be naturally occurring. It must occur in nature. This probably is galvanized steel. It's zinc and iron and carbon. That combination could occur in nature. I don't think it does, but it's not about whether that combination can occur in nature. It's whether this specific object occurs in nature. It doesn't. A person made this, and so it's not naturally occurring. This is where we get into some hazy area with synthetic diamonds. Like, synthetic diamonds are made by people in a laboratory. They're chemically and crystally identical to regular diamonds. They are solids. They meet all the other criteria, but since they were made by human beings, this philosophical idea that since a human made it, it is not a mineral. We could even say it's still a diamond, but it's not a mineral. They must be naturally occurring. What else must they be? Your book calls it inorganic. Your explorations call it inorganic instead. Abiogenic. Organic has a very specific meaning in chemistry. Organic means that it's made of, in chemistry means it's made of chained carbon. You don't want to imply it's abiogenic, which means, what's the prefix A on Greek letter, or Greek words mean? Like asexual. What? Without sex. Biogenic. What's the genic? Created by. What's bio mean? What? Living, yeah. So biogenic means without having been created by life. So cannot be created in a living process. Like what? What would be an example, a counterexample? Or I should say, what's a non-example? What's something that people might think is a mineral was created in a natural process? Sorry. Created in a living process, forgive me. Seashell. Shells are not minerals. They are crystalline, they are solid, so they are not minerals. And then lastly, it must have a specific chemical composition. Specific chemical composition. Like I'm going to just point this back to this little diagram, calcium aragonite. So in the same way we said that the same chemical composition, calcium carbonate, could refer to aragonite depending on the crystalline structure. Well, there are lots of crystals, there are lots of minerals that have this rhombohedral crystal structure like calcite, but are not made of calcium and carbonate. So both the chemical composition and the crystal structure matter for minerals. All of these are the what's of minerals? Yeah, properties. I'm even going to put in parentheses afterward criteria of minerals. I'm going to erase part of that. The criteria of minerals. These are the criteria of minerals, and they're just the criteria. What does that word mean? Yeah, a set of rules, a set of things that have to be true for us to consider it a mineral in this case. The criteria for getting an A in this class are like to get a good grade on the explorations, to do the lab. Those are criteria. Those are things you have to meet in order to get an A. In this case, these are the things that something has to meet, an object has to meet in order to be considered a mineral. Now over here we're going to talk about, I'm going to try to do this so that people watching online at Kyla Vogel can see it, properties. We are over here going to do the properties of minerals. So just to be more clear, because I had made this mistake a second ago, these are not properties. I mean, they are, but they're not defining properties of minerals. These are the criteria. And then these are the properties of minerals that we use to define individual minerals. And you already know these. What are the properties you analyze in the lab to determine what mineral is what? Hardness. Okay, let's go through them all. Hardness, let's just list them first. I'm going to spell it right, though. Hardness, luster, streak.
Color and luster.
Okay.
Because color isn't really that important.
Right.
There can be minerals, 700 million minerals.
I can think of at least two more and both of these are the most important ones, I would say.
Special properties.
Okay, we can put that. I'm going to put it at the bottom, and that's not the most important one. Special properties. It can be very handy if there are special properties, but obviously not everyone does. What are the other two that are actually the most? Based on what we defined a mineral as, chemical composition and crystal structure. They are what we call crystal habit. Your book calls it crystal shape. In real life, we call it crystal habit and cleavage / fracture. And we're going to define each one of these. What is hardness?
It is the scale of,
2.4 to 6.5.
how are they measured? Like, what units?
They're unitless. It's arbitrary. It's comparative. It's relative. Higher numbers are harder, and this is the Mohs scale of hardness. 1 through 10, Mohs scale.
And 10 is diamond.
10 is diamond. They have specific, there is a way using units to measure hardness. I don't even know what it is. I would guess it's something like pascals per square centimeter. I don't even know exactly how you'd measure. I'm sure there is a scientific numerical way to measure hardness. The Mohs scale of mineral hardness is an arbitrary scale, where 1 is talc, the softest mineral, like historically considered the softest mineral, and 10 is diamond, the hardest, although that's not true either, mineral. There are man-made and naturally occurring objects that are harder than diamond. But we use the scratch. Higher numbers on the scale, higher numbers scratch lower numbers. Fracture. Higher numbers scratch lower numbers. So if I have diamond and a piece of talc, the diamond will scratch the talc and the talc will not scratch the diamond. That's hardness. Color and luster, we already know. Someone has said before, what's true of color regarding mineral? Yeah, let's put unreliable. I was going to put useless, but it isn't really. I mean, for one thing, like the color of a sapphire is useful because that determines, like how much people like it. It's not useless, it's just not reliable. It's an unreliable identification, unreliable ID. And then luster is its shininess. And it's not just how shiny it is, it's the type of shininess. And we have some examples. Metallic. And then the rest of these are all non-metallic, which includes vitreous, resinous, oily, etc. There are lots of other earthy, dull. There are lots of them, but those are all non-metallic luster. The streak is really, what are we looking at when we look at the streak? We scratch it on a, or we don't scratch the streak plate with it. In fact, actually the streak with the streak that makes it slightly more reliable than color. What are you really doing when that jagged little streak plate is taking off pieces of the mineral? You're really looking at the mineral's what? Color of powder. Yeah, sediment's a good phrase. I would call it powder. What we're really doing is we're just making a fine layer of powder of that color. What it really does is it kind of removes luster from the equation. You'll see a lot of times that some minerals that are green or black, visually, like just the mineral black, have a red streak, or a white streak, or a blue mineral with a black streak. I mean, the streak is not uncommon at all for the streak to be a wholly different color from the color of the mineral itself. And what that is that you really find the color of the powder. Streak is much more reliable as far as most samples of the same mineral will have the same color or a similar color of streak. But several minerals still have black streak, for instance. So it's not super reliable in narrowing it down, but if you already have an idea, the streak can be a good way of confirming or rejecting that idea. Whereas color, not great. The classic thing, and I've told you this several times now, but the classic example is that almost any mineral can be black, and one specific mineral can be lots of different colors, including black. So if we have a black mineral, that really doesn't tell us a whole lot at all. Dr. Leidy, who taught me Intro to Geology at college, said that if he was being really mean, he could probably find a black sample of every mineral that we were made to identify. Like we had a test that was 45 minerals out in the classroom. You had to write down, like, number 1 is talc, number 3 is amphibole. I don't know. They're all different kinds. And he said if he was really mean, he could find a black sample of every one of those, and they'd all just be black. Every mineral, that would be mean. But most any mineral can be black, and so color is unreliable. Other colors too, not just black. Crystal habit and cleavage, these two are both great because they tell us the crystalline structure, which, remember, that was one of the things we used to define what that mineral is the crystal structure. So crystal habit is really just how the crystal grows. How the crystal grows. It only really works if we have what's called a hollow crystalline sample, where the whole crystal, it hasn't had enough time for a whole crystal to grow and complete. And then cleavage and fracture are how a mineral breaks. How it breaks. If it breaks along crystal lines, we call that cleavage. Along crystal lines, we call it cleavage. And if it breaks anywhere else, so not along crystal lines, we call it fracture. A real, get out of the way. Get out of the way, chair. My chair's in the way, I'm sorry. A real good example of this, I think, this is a mineral. Why not? Let's go through the criteria real quick. Is it a solid? Let's try again. Is it a solid? Yes, yes, it is a solid. Is it abiogenic? Obviously, who is alive. They're probably dead now, but they were alive. Does it have a specific composition? Maybe it might have a specific. Does it have a crystal structure? It probably does have some arrangement. I'm not. It's not a mineral, but I'm going to pretend it. What mineral is this like? Does anyone remember? What mineral can you flake little? Yeah, it's like mica. It's like mica. So we can pretend that this whole thing is like mica, and that the crystals are in these sheets, just like mica has one direction, one axis of perfect cleavage, where we can cleave off these sheets along the crystal lines, and it's a perfectly smooth surface underneath. You know about this of mica, right? So that would be an example of cleavage, to have it break along those crystal lines, in between where the crystals are growing. But, so there are three axes in nature, right? As a three-dimensional object, we have an up and down axis, a forward and back axis, and a left and right axis, right? So it breaks perfectly along the up and down axis. There's perfect cleavage there. But if I break it along this axis, that's fracture. And if I break it along this axis, that's fracture. Do you see? So there's three dimensions, and it can have that many dimensions of perfect cleavage. Mica has one dimension of perfect cleavage. It'll break perfectly on one crystal line, but it'll fracture on the other axes. And then, as Camden said, several minerals also have special properties like magnetism, effervescence, fluorescence, which is what she did her presentation on. So we'll let her do that. Does anyone have questions about the rest of what you did just a second ago?
So, like, mica has
One axis of perfect cleavage. Perfect cleavage. It'll break along the crystal line. Layers of the crystal apart on the crystal line. It will break, but it'll be jagged, and it won't necessarily be jagged, but it won't be along a crystal line. It won't be a perfect linear break like the cleavage. That's the real difference. Is that cleavage is along the crystal lines, and fracture is the break, not on the crystal lines. Any questions about the properties of minerals? Do you understand how? You should understand how these work. This was your last about the properties of minerals. No. Questions about the criteria minerals have. You are not for your test required to know the different kinds of minerals, but you might be aware of some examples of each of these. Like I had my example of mica for cleavage. You might think of some examples of like diamond has adamantine luster, for instance, or quartz has vitreous luster. Think of some examples of that. And then also be able to think of some examples and non-examples of the criteria of minerals. Yes? Any questions at all?